Am I audible?
Yes,
And
ma'am.
is the slide visible?
Yes, ma'am.
Okay. So we have come to the last part of Unit 3, that is automated assembly lines. We have discussed the manual assembly lines already, and we just saw the fundamentals in manual assembly line, and then the line balancing problem. And we saw the three methods in line balancing problem. Whenever there is this line balancing issue, you can either implement those three methods or any one of them and get the solution for this problem of line balancing in an assembly line. So we have seen the three types, that is largest candidate rule, Kilbridge-Investor method, and the rank position weight method. All the three we have discussed with the help of one example, but in exam or in any of your tests, you cannot just rely on that one type of problem. That is that one example. You will have to explore your textbooks in order to find different problems that can be solved using those methods, different problem statements. So your performance for the first internal, I have seen the problems that you all have solved are none of you have actually been able to solve the problems correctly, the problem which was given. And the performance of first internal is not up to the mark. The score is really very bad. So just I hope that you all will improve in the second internal. Study really well for second internal. There's less of theory, more of problems. Just concentrate well and study these problems. If you all have doubts, do contact us for any sort of difficulties if you all find in solving the problem, especially. So moving on to this, the second part of the unit 3, that is automated assembly systems. Okay, before I proceed with the contents of the syllabus, this is a very important announcement that I wish to make here, that on this coming Thursday at 2:30, I will be taking this class, and this class will be handled by an industry expert. So it will be an industry expert talk. We have Mr. Sridhar Pise. He will be giving us expert talk for just 1 hour, and that will be on Thursday on at 2:30 p.m. That is during your regular class time. Just spread this information to your other classmates also. So Thursday is 26th, that is day after tomorrow at 2:30 during your regular class hour. We will have the industry expert talk, and attending this industry expert talk, which is again going to be online, is compulsory. Attendance surely will be taken, and those who fail to attend the same may have to face the things because soon after that we have the second internal, and maybe the second internal valuation will get affected if you do not attend the expert talk. This I'm saying, seeing your response for the regular classes. So as we are inviting somebody for a expert lecture or expert talk, we just hope that there is proper coordination and cooperation from the student side also, because we are inviting somebody for this lecture. Okay, so take this really very seriously and see to it that you all attend the expert talk that is scheduled on Thursday at 2:30. Okay, so now moving on to the contents. We are going to study the fundamentals of automated assembly systems. The automated assembly systems here, what we are going to discuss is relatively very simple. We have discussed what is a manual assembly line. Now we are seeing what is an automated assembly line. Of course, the name, the statements or the names, topics itself make it very clear as to what we are going to study, or basically you can get an overview of this. Manual assembly line is where you have all the labor working in order to complete the assembly system. Whereas when it comes to an automated assembly line, you do not have human intervention to a great extent. Okay, you just have a very little human intervention when it comes to the automated assembly line. Just ignore the spelling mistakes in the slides. Okay, so what is this automated assembly system? How do you define this automated assembly system?
Assembly system which has least or no
Yeah,
interference from human.
pardon me.
An assembly system which has least or no interference from human.
Huh.
That is
Is
automated
automated
assembly system.
assembly system. Yeah, you can. So here in the slide also you can see the definitions. So it is used of mechanized or automated devices to perform the various assembly tasks in an assembly line or a cell. So when you have almost all the devices which are going to be mechanized or you can say automated, so there is very less human involvement when it comes to the assembly operations. So one thing is there cannot be any system which will be fully automated, okay, fully, completely automated. Because when it comes to these assembly systems or assembly lines, there will be maybe one or two operations which, sorry, assembly operations in between, which will require some human intervention, maybe just to have a proper orientation there will be a human being involved. So I cannot say that there is going to be a 100% automated assembly line. You can say 99% yes, it's possible, but there will be slightly, because at least to operate any of the automated systems in that case, at least to even start the system, you need a human being. And in order to program everything and to put things in line, it is the human beings who are at task. They have to do all the things, and then it's the system which is going to start just follow the instructions given by the human beings. So here in automated assembly system, we are just using the devices which will be mechanized or they are completely automated, and that they will basically help you in the assembly. So most automated assembly systems, they're designed to perform a fixed sequence of assembly steps on a specific product that is produced in a very large quantity. So these things are very important for you to remember here, that if you are having a very say the job shop production kind of a quantity, or maybe if you're going for a batch production also, automating your production line in that case, or maybe your assembly line, may not be that advantageous. So when you have a very large quantity or when you go for mass production, that's when you can justify all the investments that you make in order to automate the production of the assembly system. So we basically prefer automated assembly systems whenever you have a very large quantity or mass production that you're going to have. And also the sequence has to be fixed. There should be very less alterations that you have to do in the sequence of operations that have to be performed. So it's very important that these things are taken into consideration whenever you plan to go for an automated assembly system. So if you're having a very limited or a unique kind of a product, and if you want to go for automated system at the very start of your business, then it might not be helpful, because once you get that market idea, once you are sure that your product is accepted in the market, that's when you actually start automating the things. Your very first step always, if you come up with a new product, cannot be going for automation. So maybe starting with any new product, first you start with the manual production system or a manual assembly system. And only when you have a grip about the market, in the market with respect to your product, that's when, after knowing the market status and all, you will go for these automated assembly or the automated production systems. So as we know, what is assembly? Assembly is nothing but joining of two or more parts to form a new component. So we know that what is assembly. And yeah, am I audible?
Ma'am, the slide
Yes,
is
ma'am.
not changing.
Yes, ma'am.
Slide
Ma'am,
is
the slide
not.
is visible. It's visible, ma'am.
Slide is visible, ma'am.
Ma'am, it's not changing.
No, I have not changed it yet.
Uh,
Yeah. So as I said, we know what is assembly. Assembly is nothing but joining of two or more parts in order to form a new component. So automated assembly, what it refers to is, it is the use of mechanized or automated devices which are combined, sorry, which will combine these multiple components into a single entity. So automated assembly systems, they basically offer a very high productivity when you compare it to the manual assembly line, of course, because when it comes to automated systems, the productivity is anytime going to be more, the time required is going to be less, the quality is going to be better, there will be better precision and accuracies that can be maintained when you compare the same with the manual assembly lines. So automated assembly systems have fixed routines and can perform only fixed sequence. Yes, whenever you automate something, there are very less chances of making changes to that particular fixed sequence of operations that have to be performed. So these things have to be taken into consideration whenever you plan for the automated systems. So automated assembly systems, they are used under the following conditions. Okay, before that, we'll just read the slide. Automated assembly systems, they can also be defined as assembly involves the joining together of two or more separate parts to form new entity, which may be assembly or a sub-assembly. Yes. Automated assembly refers to use of mechanized and automated devices to perform the various functions in an assembly line or cell. Automated assembly system, it performs a sequence of automated operations to combine multiple components into a single entity, which can be a final product or a sub-assembly. Okay, so in an assembly line, it's not always necessary that you get the final product itself. Sometimes the sub-assemblies are also an output of the assembly systems that we have. These sub-assemblies may be further used again for assembling a different, for example, if you take an automobile, you will have an assembly line where you only have the engines assembled. So that's like a sub-assembly, right? It is not a complete car ready yet. So this sub-assembly is then further carried and where the car is completely assembled. So that's what we are trying to tell here, that automated assembly line may result in a final product or it can even result in a sub-assembly. Example could be a automobile. So automated assembly systems, their application characteristics. Um, where is this automated assembly system appropriate? When do you use it? Right? Under what conditions are you actually going to go for these automated assembly systems? First of all, there has to be a very high product demand. As I said, when your product demand is good, basically this point is important here because you have to justify the investments that you're going to make. Whenever it comes to an automated system, there's a huge investment that goes in, and if you're not able to justify the investments that you make, there is no point in going for all these automated systems. So when can you justify that? When you have a very high production rate, or when you have a very high product demand. Because when it comes to automated system, the unit cost is going to be less. There's so much of investment, initial investment that you do, and which results in the unit cost reduction. So basically that can justify that whatever investments we are making, your unit cost for production is going to be less. At the same time, your selling price can be more to some extent because you are going to give a better quality to the customers. So you have to justify the investments that you're going to make when you take a decision to go for automation. Then nextly, there is this stable product design. Now, what do we mean by stable product design? That is, there has to be minimum product design every now and then. Whenever we talk about mass production, or yeah, when we talk about this mass production, of course, we want the same type of part produced in a larger quantity. So there has to be minimum product design change that can be made here. So we have to see to it that there will be less changes and modifications in the product design. Next is the assembly consists of no more than a limited number of components. So if you're having a large number of components going in, then the automated assembly line is going to be a very large one, and it becomes a very complex and a complicated system. So when you want to go for an automated assembly line, then you'll have to see to it that you will have limited number of components going in order to make the complete part. And lastly, it is the product is designed for automated assembly. So the product that we are going to consider, it must be specifically designed for an automated assembly process. So you have to understand the complete automated assembly process, and based on that you have to plan the product. Or if you have a product, you have to see what are the constraints that you will come across when you want to go for this automated assembly line, and based on that you have to take your decision whether you want to go for automated assembly systems. So these 4 points or these 4 conditions need to be taken into account when you want to take a decision that you want to go for these automated assembly systems. So first of all, the product should have a high demand, which will result, which you are going to basically plan for this mass production. Then there should be very minimum change in product design that you do. You have to see to it that there will be less number of components which will be put in order to assemble the product. And the product is designed for an automated assembly, specifically designed for that. So the overall size of an automated assembly system, it will be less if you compare it with the transfer lines. Okay, we have seen the production lines. If you compare the yeah, so here it is, automated assembly systems and the transfer lines. Now we have seen the transfer lines earlier, the production lines, and now we are talking about the automated assembly lines. So let us just try and understand what is the difference, how both are different from each other. Okay, here basically work parts produced are smaller in size compared to the transfer line. So when we talk about a production line or a transfer line, of course, you have the actual operations to be performed. So you have a huge setup with respect to the production lines. But when it comes to the assembly lines, they are going to be comparatively smaller in sizes. The setups that we have are going to be comparatively smaller in sizes here. And the assembly operations do not have large mechanical forces and power requirements. Of course, just imagine a production operation that has to be performed, for example maybe some machining operation. So you know what is the kind of force or the power that will be required in order to machine a component. Okay, as compared to an assembly operation where maybe just a fastener has to be used or some adhesive has to be applied, or very simple assembly operation has to be performed. So basically assembly operations, they do not have large mechanical forces and power requirements as compared to the transfer lines. So size here is very less compared to the transfer lines. Of course, the space that is occupied, again, if you compare, transfer lines is going to have a huge requirement of space as compared to the automated assembly systems. And also the devices that we are going to use are going to be uh, less in, the size is not going to be very complex, or it will not be a very bulky setup that we have as compared to the transfer lines.
Ma'am, the slide is not changing.
Yeah, I haven't changed it.
Ma'am, it's in only first slide, like automated assembly system.
It is in the first slide itself.
Yes, ma'am. Now it has changed.
Okay. Now you
Ma'am,
can see.
when you go to presentation mode, it will not be changing, ma'am.
Now,
Now it's in assembly processes in automated assembly. Slide 8.
okay. So this is visible.
Yes, ma'am. Now it's
Uh,
changing.
okay. Now I have not put it into the presentation mode. Without
Yes.
presentation mode, if I'm changing, is it visible?
Yes, ma'am.
Okay. So I'll just keep it like this only. So we have these advantages of automated assembly systems. One is it gives you high production rate. high product quality and precision, low cost of production, not create the risk to the operator. Of course, if you're having an automated system, one of the advantages of an automated system is safety to the laborers, right? So you're not creating any risk to the operator. And these points we are very well aware and already have been discussing many a times. There will be a high production rate, high product quality and precision, accuracy also. Then there will be a low cost of production. As I said, the unit cost that we are talking about will be less. So what are these typical products? Some examples we have just listed here. One is alarm clock, there's door mechanism, gearboxes, ball bearings, small electrical motors. So these all products that you see here, they are basically assembled via automated assembly line. You have number of videos that you can come across. Even if you use YouTube and all, there are so many videos that you will get wherein you can see all these products actually being assembled. Okay, so like this you'll have many other examples also. But when it comes to these automated assembly line products, or products that we're talking about, they're the ones which are these small products. Okay, even if you consider most of the components that you see in the market also, they may not be completely automated. Okay, there will be some which will be semi automated type. So you have to just have a complete proper look into it. And also as I said, there are these number of conditions that we need to keep into consideration. You have to consider, and based on that only you have to take a decision to go for these automated assembly lines. So based on that, you have some products listed here which are assembled on an automated assembly line. So what are these different assembly processes in an automated assembly? We have adhesive bonding, that is applying some adhesives, snap fitting, spot welding, stitching, stapling, riveting, screw fastening, placement of components, soldering, insertion of components. These are just a few processes which have been listed here. These are all examples of these assembly operations where one part is joined to the other part in order to complete the product. So as you can see, all the ones which are listed here are basically going to help you to join the parts from join one part to the other part. So like this, you may have many other type of many other processes as well. So these processes that you can just see, if you can imagine, there is very less force that is actually applied when it comes to all these processes which are listed. So you can actually have a comparison of these assembly lines with the transfer lines, which I just told you, the comparison between an automated assembly system and a transfer line. So if you can see the second point, assembly operations do not have large mechanical forces and power requirements. So this point justifies if you see is justified if you see the different processes, assembly processes that I just listed. So there is very less mechanical force and power that will be required. So what happens in an automated assembly system? The base part, it is going to be placed on the transfer line initially, and all the other parts, they will be added to that base part such that the assembly will be completed at the end of the line. So always you'll have the base part, or maybe some sub assembly will be placed, and to that you'll have many other parts which will be added in order to complete the product. Yes, design for automated assembly. So some principles that can be applied in product design to facilitate automated assembly. What are those? So what happens is, the product which are to be assembled on an automated assembly system, they must be properly designed to suit the system. Okay. So following what are listed here, these are some of the important points which we need to consider in order to design the product for an automated assembly system. What are these? First is reduce the amount of assembly required. What do we mean by reduce the amount of assembly required? So as it is already said, you are going to try and reduce the number of parts that you are going to, or number of components you are going to use in order to assemble the product. Next is use modular design. Now, what do we mean by use a modular design? The number of steps which are basically involved in making an assembly of a product, it must be reduced in order to decrease the downtime. So use these modular designs which are not going to be very exhaustive and complicated type. You are going to try and make uh, the steps basically which are involved in making the assembly of the product. They must be reduced in order to decrease the downtime. So also the design of the product. It must be modular. What do we mean by modular? It must be such that each module will have a maximum of 12 to 13 parts, which are to be assembled in a single station assembly system. So you can use this modular design system wherein you have the complete assembly in form of modules. One module will have 12 to 13 parts, which are going to be assembled at a time. And later on, these modules can again be assembled in order to make a complete assembly. So you can go for this modular design, usage of this modular design. Next is to reduce the number of fastening elements. Okay, or it is to reduce the number of fasteners which are required. Now we know what are these fasteners. I suppose everybody knows what are these fasteners. They are nothing but the screws and nuts that we are going to use to join one um, plate to other, one component to the other. So instead of using a number of fastening elements, like maybe the screws, nuts, and some similar fasteners, provisions must be made in the component design for snap fit or similar designs, which may reduce the necessity of fastening elements. So if you have seen what is a snap fit, okay, I haven't got anything to show you what is the snap fit, but you can actually use this type of fastener instead of going for these extra nut and bolt type of arrangements. We get these snap fasteners, snap fits, which are available. We can actually design it in that way. You go for those type of fasteners. So instead of just using more number of fastening elements, you go for some alternate methods, some alternate provisions which are available. Use those. So also the product must be designed such that several components are fastened simultaneously rather than each component is fastened separately. So that also has to be taken care of. You see how the fastening can be done simultaneously instead of each fastener getting fastened at every time. So some simultaneous operations also should be considered here. Next is reduce the need for multiple components to lie handled at once. So instead of handling multiple components at once in a particular assembly system, the work should be distributed to different systems. So you can have yeah. So instead of having these handling multiple components at once, you can have the work being distributed at different systems. Next is limit the required directions of access. When we are going for these automated assembly systems, the direction of access, that is, of course, when it comes to an assembly line, the orientation and the direction of the component that has to be assembled, it's very important. You just cannot place the component anyhow. It has to have a certain orientation given. There has to be a certain direction that has to be followed in order to assemble. So you have to limit the required directions of access. So you'll have to fix the direction of access. So the component, they must be added to the base part in a particular direction itself. Okay. So it should be appropriate if all the components are added vertically from above to the base part. So you'll have to fix one direction for all the parts to come from one direction itself, instead of having this random direction of access in order to assemble these different components to the base part, you can plan the direction of axis in one direction itself. For example, you can just have the base metal and all the parts or the components that need to be assembled, they can start getting assembled in a vertical direction. You start allowing the components to flow down in the vertical direction itself. So you can fix that one direction of axis. Next is required high quality in components. Yes, this is very important step because the quality of the components that you are going to assemble have to be up to the mark. It has to be good quality itself. Because what happens if the quality of the components is poor, so the poor quality of the product, it can even jam the assembly systems, and also it can affect the overall quality of the assembled products. Because after this, after a little more discussion, we will come across the part delivery system, okay, wherein you will see that you are not going to do these alignments or orientations manually. All these will be done with the help of certain devices. So in those devices, if the quality of the components that you're going to put is not good, it can jam or clog those devices, okay, leading to halt of the complete assembly system, or it can even finally lead to a poor quality product also. So quality of the components that you are going to use for these assembly operations have to be good. It requires a very high quality components. So a consistent good quality of product, it must be added for high performance of an automated assembly system. And next is implement hooperability. So as I said, we are going to study about the part delivery system. So implement hooperability means what? Hooper, basically, what is this hooper? Hooper, it is a device which is used to feed the parts to the assembly station. So it's a very important first step in the assembly system. It is a device which will help you to feed the parts to the assembly system or the assembly stations. So the part must be designed such that they should be suitable for hooper and must be able to flow easily. So I will show you what is an hooper. If you're going to keep a huge component, maybe a very heavy and a very bulky component into that hooper, there is no point in having that hooper. It is not going to help you to perform any task itself. So you have to plan the product that has to be assembled in such a way. You'll have to plan things in such a way that you can use a hooper, and there are these parts which can be accommodated in that hooper, and that hooper can actually do its task. So considering all these things is very important when you plan the automated assembly system. So if you're going for an part that needs to be assembled using an automated assembly line, you have to give it a thought about all these design considerations. Okay, reduce the amount of assembly required, use modular design, reduce the number of fasteners required, reduce the need for multiple components to lie handed at once, limit the required direction of access, require high quality of components, and implement hooperability. So these are some of the design considerations um, when you plan for an automated assembly system of a product. Shall I proceed? Any doubts?
No, ma'am.
No, ma'am.
Okay. Next is yet another important and interesting and this topic which we have already come across in the automated assembly lines, but maybe a little different from those. That is a system configuration. So we are all very well aware of what do we mean by system configuration. It is nothing but just the different types in which all the elements of a system can be arranged. So system configurations, here we have four type of configurations. This is an important question. Kindly practice all these diagrams well, and some description with respect to those diagrams and these different systems that we have. Sorry, different configurations that we have. First is inline assembly machine, dial indexing machine. These two you are aware because the same you have seen even in the production lines, automated production line. Third is the carousel assembly system, and fourth is single station assembly cell. Now let us see one by one. What is inline assembly line? Simple, just like production of the inline production system, you have the inline assembly machine. That is a series of automatic workstations which are located along and inline transfer system. So you can have the starting base part, it enters, it is there on this material handling system or the transfer line that we have. And then you have these different assembly stations. ASBY represents assembly. If this was PROD, then it was a production system. AUT means automation. If it was MAN, it is manual assembly station. If it is AUT, that means it is an assembly station which is automated. So these assembly stations which are automated, they will have these components which are shown here, which need to be added in order to complete the product, in order to assemble the product. So this is inline assembly machine that we have. So in inline configuration, it basically consists of series of workstation in a straight line as shown in this figure. Continuous, synchronous or asynchronous transfer systems can be used in this inline type of configuration. We also have these segmented inline configurations, which will consist of more than two or more straight lines, which will be arranged and they will be either perpendicular to each other. For example, you have these L-shaped, U-shaped, rectangle. So all these configurations we have already seen in automated production line. It is nothing different from those. It is going to be the same. Only what differs is this: you don't have the production stations, rather you have the assembly stations here, right? So this is the inline assembly machine or inline configuration. So you have inline, you also have segmented ones. In segmented, you have L, U, and rectangular types. So this is an example for an inline assembly machine. You can see all the stations that you see here, and they are all in a straight line. Here also. Next is dial indexing machine. So the base parts are loaded onto fixtures or nests attached to a circular dial table, and components are added at workstation located around the periphery of the dial as it indexes from station to station. So we have already studied what is a dial indexing machine or a rotary configuration. We have already seen that you have this table which is going to move. There are these dial indexing mechanisms that we have seen. Using those mechanisms, there is the shift of um, the work part that takes place from one station to other station. But instead of production stations, you have these assembly stations here. It is the mechanism here is going to remain the same. So in a dial type assembly configuration, the base parts are placed on a circular table, which is called as a dial. So you have this dial shown here. The workstations are placed around the periphery of the dial. You can see these stations which are placed around the periphery of this table. As the dial rotates, the components are added to the base part. Synchronous and intermittent motion transfer systems are used with dial type assembly configuration. So sometimes dial type configuration, they are designed to use continuous transfer systems. For example, if you consider the bottling plant, if you have seen those, the bottling plants that are there, they also have this continuous type of transfer system, material transfer. Okay, so basically, mainly it is the synchronous and the intermittent motion that is followed here, but also continuous in some rare applications can be used. Also, in this we have seen how to calculate the angle of rotation or the dial indexing that has to be done. It all depends upon the number of stations that are going to be placed. So based on that, you can actually calculate all of that. So what you see here is a 1, 2, 3, 4, 5, 6. This what you see here is a 6-station rotary dial machine that is there, dial indexing machine that you see here. So this is one dial indexing machine that you see. Next comes is the carousel assembly station. This is a little new for you all, but it's very simple to understand. This is a hybrid between circular workflow of dial indexing machine and straight workflow of inline system. So it is a combination of two. You can see you also have these circular transfers taking place and also the linear transfers. And you have all these stations which are going to be placed at their periphery. So carousel system of configuration, it's simple. It's just the combination of the inline type and the rotary type. Yeah, what you see here is not an assembly system, of course. This is like a storage system that you can see here. You see these racks and all. But this is how a carousel configuration looks like. Okay, this is not an assembly station. This is not at all an assembly station. This is a storage station. You can see all these boxes, these rack kind of things here, where you are actually going to store the parts. But this is the configuration. You can see how it is. You have them moving along the. You have all these stations in place, and you have the transfer line that is there, which is going to move in this configuration. Okay. Moving on to the last configuration, that is single station assembly cell. So assembly operations, they are performed on base part at a single location. A robot is sometimes used as the assembly machine. So we have the starting base part, you have the assembly station, and you have the completed assembly. So in a single station assembly configuration, the assembly operations are performed at a single location. What happens is in this system, the base parts are placed at a particular location. You can see it is placed at a the base parts are going to be at a particular location. It has its entry from one side. The individual components are added gradually till the completion of assembly, and the entire assembled component is removed from the workstation. So you have this base part, it comes here, and at this station itself, one by one, all the parts are going to get assembled here itself. This base part need not move from one station to other station. At one station itself, all the components, different components are going to be added in order to get the final completed assembly. So this type of assembly system is slow when you compare it to all other type of configurations, because everything is happening here itself at one station. There has to be entry of one component, then there is entry of another component. This component, a base part which is there, it will be there itself. Suppose if there are some direction changes or orientations that have to be changed, everything has to be done at this one station itself. So it takes comparatively more time um, to the other configurations that are there. So these are the four configurations that we have: inline, rotary, carousel type, and the single station assembly cell. So multi-station versus single station. If you consider the inline, rotary, or the carousel type, they are all the multi-station assembly machines or multi-station assembly lines. And what we saw here is a single station assembly cell. So comparison of these two: multi-station, it has faster cycle rate, high production quantity, more operations possible, more components per assembly. Whereas a single station, it is suited for robotic assembly, intended for low production quantities. Shall I continue, or you want to break for 5-10 minutes?
Madam, continue.
Okay, because I'm just left with the last part of discussion. We can just finish it off. So till here it is clear.
Yes, ma'am.
Yes, ma'am.
Now coming to the most important part of today's discussion, that is part delivery at workstation. So when you want to completely automate something, it's part delivery. The start, the first step itself has to be very correct, right? So everything has to be automated. That means even the way the parts are going to get oriented, the way they are going to be placed, everything has to be automated. So how is all that possible? It is possible with the help of this part delivery system. So a typical part delivery system at a workstation, it consists of the following hardware components. First is a hooper. As I said, one of the design consideration is hooperability, right? You should have the ability to accommodate this hooper at the start of your assembly line. So first component of a part delivery system is a hooper, which is basically a container for parts. It is going to have all the parts which have to be assembled. It should be able to hold them. Next is a part feeder. It removes the parts from the hooper. Next, a selector or an orienter. It assures the parts in a proper orientation for assembly at workheads. Next is feed track. It moves the parts to assembly workhead. And last is escapements and placement devices, which remove the part from feed track and place them at the station. So, very important very important question as well. Sketch and explain the part delivery system at an automated assembly line. Okay, you will have to sketch the diagram. You can see the diagram is here. You'll also find this in the book. This is taken from the book itself. So you can just see what you see here. Just don't take this as some overhead tank and there is some flow pipe which is attached and then there is something going on. No, this is not actually how things are in the assembly line. There is just this hooper in place which is going to help you to hold all the parts that need to be assembled, and those then will be sent into the selector. The selector is taking the parts from this hooper, and then it goes into the feed track. It will correctly orient it and then send it ahead. And these escapements and placements which are there, they will be taking it out from this feed track and placing it on this base part for assembly. So the parts of an typical part delivery system, hardware components, they are hooper, part feeder, selector and orienter, feed track, escapements, and placement devices. So now let us see all of these one by one. Okay, hooper. Hooper, it is the container into which the components are located at the workstation. A separate hooper is used for each component type. The components are usually loaded into the hooper in bulk. This means that the parts are randomly oriented initially in the hooper. So you can actually imagine a hooper to be something like a tapered container. In that you're going to put all the components. Of course, the similar components, not some random different components, because the complete assembly line, the part delivery system that is there, it will be designed for that particular component itself. Okay. For example, suppose if you want a nut to be directed at the assembly station, you cannot have the part delivery system designed for a bolt, because there are these constraints with respect to a nut. There will be different constraints with respect to a bolt. So based on that, what is the part that needs to be assembled, you are going to have the complete part delivery system design. So basically, what is a hooper? It is a container which contains the components, which the components are located at the workstation. So there are these different types of hoopers that we see. Sorry, I'll just show you the diagram. Okay, so hooper basically is nothing but just a tapered kind of a structure which is there, which is going to help you to hold all the components. Next is vibratory bowl feeder. Okay, so as we said here, the next part is a part feeder. So what is this part feeder? We have one of the examples, which is a vibratory bowl feeder, part feeder. Part feeder, it is a mechanism that removes the parts from the hooper one at a time and directs them into the selector and orienter. The part feeder and hooper mechanisms are usually combined into a single mechanism. So this is very important. What you see here is a combination of part feeder and hooper. So this region that I'm talking about, this part, it is the hooper. Okay, and you have this part feeder, which is going to be somewhere here. So this, what you see, is a vibratory bowl feeder hooper, which is going to hold all the parts, and with the help of these vibratory bowl feeder which is there, you'll have all the parts following a certain path and coming out, and that goes ahead or goes further into the selector or the orienter. Okay, so this is the complete mechanism of this vibratory bowl feeder that is there. So this is the most versatile of hooper feeder for small parts. It consists of bowls and helical track. Parts are poured into the bowl. This is nothing but the hooper. Helical track moves parts from bottom of the bowl to the outlet. So you can actually imagine this complete setup to be vibrating, and you have all the components placed here. With the help of those vibrations, you see that all those tiny parts, small parts, they follow a certain path and it comes out of the outlet, getting oriented or moving ahead to the selector or the orienter. I will also show you a video of the same. I hope it will be helpful for you to understand this. Next is vibrations applied by electromagnetic base. Oscillations of bowl is constrained so that parts climb upward along the helical track. So we are basically going for the vibratory bowl feeders here. Of course, the oscillations are going to be constrained here so that there is one upward movement itself taking place, so that those small tiny components, they can follow one single track which is given and move ahead. So this is a vibratory bowl feeder. Next is a selector and an orienter. The purpose here is to establish the proper orientation of the components to the assembly workhead. So what is a selector? It basically acts as a filter. Only parts in proper orientation are going to be allowed to pass through the feed track. So you can see here is a selector. What does the selector do? There is the part enters from the hooper feeder mechanism that is there. From there, a part enters in. Then you have a certain restriction or a constraint here. If it fits into it, it will allow it to go ahead, else it will drop it down. So if it passes on, it is now going to move ahead. So suppose now these are the circular, you can see these are something like a nut. Okay, if they are going to satisfy the condition, it will be moved ahead. Suppose if this is not a complete circular component, and if it is having a cut in between, so as it comes here, it will fall down from here. The one which is complete, it will move ahead and it will move to the feed track. So this selector which is there, it is basically acting as a filter. Okay, it will act as a filter. Only parts in proper orientation are allowed to pass through to the feed track. Next is what is an orienter. It allows properly oriented parts to pass. Orienter orients parts that are not properly oriented. So here you can see this is an orienter. So what it will do, it will orient the part in the proper orientations. So here you have this, you can see this is placed flat like this. This is a square block which is placed flat, but it basically needs to be held in this way. This is how the orientation is. So with the help of this orienter, this can be, the orientation of this block can be changed here. So you have certain constraints in between. The design will be in such a way that the parts will be, as in when it glides over it, it is going to have a proper orientation. So these are the selectors and orienters. One is basically going to filter the components, and second will give a proper orientation as required for the assembly. Next is feed track. It moves the parts from hooper to assembly workhead. Categories are, you can either have gravity or powered. Gravity hooper and feeders are located at a higher elevation than workhead. So you can see this diagram that we have shown here. This basically has a gravity feed track, because the components will move from here and they will straight away with the help of gravity move downwards. Or you can even have a feed track which will be powered. Power basically uses air or vibrations to move parts towards the workhead. Um, yeah. Escapements and placement devices. Escapement devices, they remove the part from feed track at time intervals that are consistent with the cycle time of assembly workhead. Placement device physically places the parts in the correct location at the assembly workstation. So here you can see what is an escapement. Escapement and placement devices. So this is escapement, and they're not separate, they're escapement and placement device. One is horizontal, what you see here, and one is the vertical device for placement of parts onto the dial indexing table. Okay, so what is the purpose of this mechanism? It is to remove the parts from the feed track at regular time intervals and place on the assembly station. So you have this, which are the parts that have to be placed on the assembly station. So here you know this is a dial indexing table. So you can see this is a dial indexing table, and this escapement and placement device which is there, it takes the parts and it is going to feed it correctly to that particular station. Okay, so here also you can see this is a vertical a feed track that we have seen here, and this is a rotary indexing table that we see. So with the help of these escapements and placements that we have the proper placement of the parts taking place on the work table. So escapement and placement devices are sometimes the same device, sometimes the different devices. So escapement of rivet shaped parts actuated by work carrier. So you can see this is a little slant tilted type, and these are the parts. Okay, and these are the work carriers. So with the help of this spring blade escapement, when this component it comes here, this will be pushed, and this red color rivet kind of a part which is there, it will get placed on this, and it will further take the parts. So escapement and placement devices, two types of pick and place mechanisms for transferring base parts from feeder to work carrier. You can see here again, these are just some, this is linear type. It will pick the part from here, retract, go back, place it here and come back. And this basically, this is a work carrier, will take the parts and move ahead to different stations. Likewise, here you have this material handling system or a robotic arm that is there, a pick and place unit, which will have a rotary motion, which will have, which will move, take an arc, take a turn, or it will move orthogonally. Sorry, it will move by 180 degrees and place it at the work carrier. So these are the different components, hardware components of a part delivery at workstation. There are different mechanisms which are available, like either you can go for the gravitational one, or there can be some powered, power supported mechanisms that we have in place. So I will quickly show you one video. Let's see if that can be helpful. This video basically, if you just Google few videos, you will get many such videos, and you will be able to understand things in a better way. You can just see how the things are actually in the, how they are actually used in industries, and how complex and complicated they actually are. Okay, so okay, so is this visible? Is it
Yes, ma'am.
visible?
Yes, ma'am.
So like this, you can see a number of videos. I've just so this is a vacuum cleaner brush automated assembly line. You can see the conveyor belts. which are used for moving the components from one station to other. These are all the parts which need to be assembled. See, there is human intervention. Again, you have a person who is doing the very first step. Here, you're not using this part delivery system because that is more suitable for smaller components. So this is another, can you see the vacuum grippers? Then there is this printing that has to be done on it. There are these vacuum grippers, the gray color ones that you see here. See how it is getting assembled. So there has to be some force. Here you see a hooper. See, this is a hooper. A hooper and a part feeder. So this is a hooper which is going to have all the components in it. And can you see this path that is there? This is a part feeder. So because of this vibratory motion, these parts are going to follow a certain track and they will be taken out. And it will be fed further to the selector and the orienter. So that's how it is. You will get many such videos. Please try and see those. So you can see these conveyors here. Wheel assembly station, you have the vacuum cleaner wheel getting placed. See, these are the wheels are attached. Wheel clamping, force control, there is proper clamping of wheels that will be done. Marking station. See the vacuum grippers, how they lift it. This is the unloading station where you have the sub-assembly of this vacuum cleaner made ready. And of course, there are some operations, some processes which have to be performed manually. This is also another, this is a production assembly video. This is of the Bentley car. See this. Here you cannot use a part delivery system. See how it is getting assembled. Is it visible?
Yes, ma'am.
Yeah. So such videos you all can see on YouTube. See, there is some lubricant which is sprayed inside. You have the pistons, cylinder arrangements. See how things are assembled, the amount of precision and accuracy that is required, the fastening that is done. So this is all an assembly operation itself. You can say this is like semi-automated. Material handling and all has to be done by these uh, powered conveyors, overhead trolleys, and see, this is automated. So what part of an automobile is this?
Ma'am, engine block.
Yes. So as I said, everything cannot just be assembled at that point of time. So this is like a sub-assembly. This will then go into the automobile. This engine block will then be fixed into the chassis, and the other, the complete body of the automobile will be made ready. So of this particular assembly line, this is the product. This is the output that you got. This is a sub-assembly. So this is okay, there's some ad coming up. So I'll close the video here itself. Like this, you will have a number of videos that you can see on YouTube. You can also see some videos with respect to, see, this is a Ford moving assembly line, the complete vehicle assembly you can see. So just check for such videos. Yeah, this is a more relevant video with respect to the part delivery system. Can you see this? This is the Hooper and the part feeder. Okay, Hooper and the part feeder. You can see all these tiny components here, and then you see the pathway that they follow in order to come out and go towards the selector and the orienter. Then it comes into these part feeders. In this itself, you'll have the orienter selectors. They will be oriented in a certain direction when it comes out. Then you have these robotic arms and all, which will take it further. And the complete assembly system is here in place. Okay, so y'all can just take reference of these videos, see watch such videos and try and understand, or just you can just get a reference of whatever you all have in your books, in your syllabus, how things are actually being used in the industries. And yeah, whatever we study are to the very basic levels. There is a lot of uh, things that you all can explore and understand how complex the systems actually are when it comes to the automated systems. Okay, so I think we can stop here. This completes the unit 3, and we can have the unit 4 started in on Friday if possible, or else after your internals, that is next Thursday, Friday. Okay, so as we are going to miss our classes on Monday, Tuesday because of your internals, we will have the class on Thursday, Friday next week. And on this week, in this week, that is on Thursday at 2:30, you will have the industry expert talk. Please convey this to all your batchmates, your classmates. CR, it's your responsibility. Nikhil.
Yes, ma'am.
Okay. So shall we stop here?
Yes, ma'am.
I will try to share all the videos today. As I said, I have some problem sharing the videos. It shows some error all the time. I'll see how best I can rectify that. And I'll try to share the recordings of all the classes